What exactly moved beneath Western Colombia on August 10, 2026? Why did a magnitude 7.4 earthquake rupture more than 100 kilometers, or roughly 68 miles underground, far below the shallow boundary where the Nazca Plate meets South America? And why did such a powerful earthquake strike in a region where earthquakes of this size have historically been uncommon? The most important question may be the one that cannot yet be answered. Was this earthquake an isolated rupture inside the descending Nazca Plate, or could it eventually be reclassified as a foreshock if an even larger earthquake occurs nearby? There is no evidence at present that a larger earthquake is coming, but the unusual depth, location, and faulting style make this event scientifically significant enough to deserve close attention. The earthquake struck approximately 5 kilometers or 3 miles south of San Jose del Palmar in western Colombia at 12:34 UTC on August 10th. Its reported depth was approximately 110 kilometers or about 68 miles. That places the rupture far below the shallow crust and well inside the region where the oceanic Nazca Plate is being forced downward beneath the South American plate. Earthquakes at these depths are generally classified as intermediate depth earthquakes. They are fundamentally different from the shallow earthquakes that rupture faults near Earth's surface and from the enormous megathrust earthquakes that occur along the plate interface offshore. In this case, the available focal mechanism indicates primarily strike-slip faulting, meaning that large portions of the hidden fault moved sideways relative to each other during the rupture. The location is particularly important because Western Colombia occupies a complicated part of the South American subduction system. Offshore, the Nazca Plate is moving generally eastward and descending beneath South America. That process has been occurring for millions of years and is responsible for much of the tectonic deformation that built the Andes. The plate does not simply disappear beneath the continent in a smooth downward motion. Instead, it bends as it enters the mantle, and that bending generates enormous internal stresses. Once the slab is descending, different sections can experience compression, extension, and sideways shearing. The August 10th earthquake appears to have occurred within that deforming slab rather than directly along the shallow boundary between the two tectonic plates. That distinction changes the entire interpretation of the earthquake. A magnitude 7.4 earthquake on the shallow subduction interface could represent a major rupture between the Nazca and South American plates, potentially displacing the seafloor and creating a tsunami. The August 10th earthquake was different. Its depth indicates that the rupture probably occurred within the descending Nazca Plate itself. The slab had already traveled beneath the continent before this section suddenly failed. Instead of two plates slipping directly against each other along their main boundary, rock inside the descending plate fractured and moved along a fault. It is therefore better understood as an episode of internal deformation within the subducted oceanic lithosphere rather than a direct rupture of the main megathrust interface. The earthquake's focal mechanism provides another important clue. The available solutions indicate that the rupture could have occurred on either a steeply dipping oblique reverse and left lateral strike-slip fault or a moderately dipping fault dominated by right lateral strike-slip movement. These alternatives reflect the unavoidable uncertainty involved in determining the exact fault plane from seismic waves alone. What they have in common is significant horizontal movement. The earthquake was therefore not simply a straightforward vertical collapse or thrusting event. Instead, the rock experienced strong shear, with one portion of the fault moving laterally relative to another. That type of deformation can occur when a descending slab becomes mechanically complicated as it bends, stretches, and adjusts to the surrounding mantle. The size of the earthquake also deserves closer examination, because maps can make major earthquakes appear deceptively small. A seismic map usually marks the earthquake with a single circle at the epicenter, but a magnitude 7.4 earthquake is not a point. The rupture spreads across a fault surface. For an earthquake of this magnitude and primarily strike-slip character, a representative rupture could extend approximately 105 kilometers or 65 miles in length and roughly 15 kilometers or 9 miles in width. That means a hidden fault surface potentially comparable in area to a large metropolitan region participated in the sudden release of strain. The earthquake began at one point, but the rupture propagated across a much larger section of the slab. This is also why the depth of the earthquake matters so much. At roughly 110 kilometers or 68 miles, the rupture occurred under enormous pressure and at temperatures far higher than those found near the surface. Rocks behave differently under those conditions. Minerals can change structure, fluids can be released from minerals during subduction, and the mechanical properties of the slab evolve as it descends deeper into the mantle. Scientists still debate the precise mechanisms that allow large earthquakes to occur at intermediate depths. Bending stresses, dehydration reactions, mineral transformations, and internal cracking may all contribute. The August 10th earthquake provides another opportunity to examine how these processes interact within one of the world's most active subducting plates. Intermediate depth earthquakes are actually a familiar feature of the South American subduction system. Large earthquakes have occurred at depths well below the shallow plate boundary throughout the Andes. Similar events have been recorded beneath Ecuador, Peru, Bolivia, and Chile. These earthquakes demonstrate that a subducting slab remains capable of significant internal deformation long after it has passed beneath the overriding continent. The descending plate carries oceanic crust and mantle lithosphere downward, but it does not behave as a perfectly rigid block. It bends and fractures along its journey. In some regions, intermediate depth earthquakes form recognizable zones that trace the geometry of the slab. The August 10th earthquake occurred near the northernmost portion of the South American subduction system, where this type of deeper seismicity is observed. The broader seismic setting is visible in the earthquake map provided with this event. It shows a dense zone of earthquakes extending along the western margin of South America, with different colors representing different depths. Offshore, numerous shallow earthquakes outline the plate boundary where the Nazca Plate is descending beneath the continent. Farther inland, deeper earthquakes follow the descending slab. The map also highlights major historical earthquakes, including the magnitude 8.8 event of 1906 near the Colombia-Ecuador coast. That earthquake occurred in a completely different tectonic environment from the August 10th event. The 1906 rupture was associated with the shallow subduction interface, while the new earthquake occurred deep within the descending plate. The difference between these two types of earthquakes is critical when considering future hazards. A shallow megathrust earthquake can rupture hundreds of kilometers of plate boundary and potentially produce enormous displacement of the ocean floor. That can generate a tsunami capable of crossing an ocean basin. An intermediate depth earthquake inside the slab behaves differently. Its seismic waves can still produce widespread shaking, but because the rupture is far below the surface, the intensity immediately above the earthquake is generally lower than it would be for an equally large shallow earthquake. At the same time, the depth allows seismic energy to spread across a broad region. Communities hundreds of kilometers away can feel the event strongly, even though they are far from the earthquake's hypocenter. The human impact of the August 10th earthquake demonstrates why intermediate depth does not mean low hazard. Reports following the earthquake described widespread damage across western Colombia, including collapsed and damaged buildings, injuries, and fatalities. Communities in Choco face particular difficulties because of the region's mountainous terrain, dense vegetation, and limited transportation infrastructure. Larger cities including Cali, Pereira, and Manizales also felt the earthquake and reported damage. Structures can respond very differently depending on their construction, age, foundation conditions, and local geology. A deep earthquake may distribute shaking widely, but vulnerable buildings can still fail when subjected to the intense seismic waves generated by a magnitude M7.4 rupture. The earthquake also highlights the importance of local geological conditions. Seismic waves do not affect every location equally. Soft sediments can amplify certain frequencies of shaking, while hard rock can respond differently. Mountainous terrain introduces additional hazards such as landslides and falling rocks. Older structures may not have been designed to withstand strong seismic motion. In Western Colombia, these factors combine with a complex landscape and widely separated communities. The result is a hazard pattern that cannot be understood simply by drawing a circle around the epicenter. A deep earthquake can affect a remarkably large area, and the severity of its consequences depends on much more than distance from the point where the rupture began. The internal structure of the Nazca Plate makes the event especially valuable for scientific research. The plate begins its descent offshore and continues downward beneath South America for hundreds of kilometers. As it sinks, pressure and temperature increase. Oceanic rocks contain minerals that can store water, and some of those minerals become unstable as they reach greater depths. Their breakdown can release fluids into the surrounding rock. Fluids can influence the strength and frictional properties of faults. At the same time, the slab bends and stretches as it follows its downward trajectory. These processes create a complicated environment in which earthquakes can occur far below the depth of ordinary crustal faults. Strike-slip motion within such a slab may reflect internal shearing generated by that complicated geometry. The Nazca Plate is moving broadly eastward relative to South America, but individual sections of the slab do not necessarily experience stress in exactly the same direction. Bending can rotate the orientation of stress. Variations in slab thickness and temperature can produce different mechanical responses. Interactions between the slab and surrounding mantle can also contribute to deformation. The result is a three-dimensional system in which a fault can experience sideways shear even though the plate as a whole is being forced downward and eastward. The August 10th focal mechanism provides evidence of exactly this kind of complicated internal deformation. Colombia is particularly interesting because it lies near the northern end of the Andean subduction system. The tectonics here involve more than a simple boundary between two plates. The Caribbean plate interacts with the northern Andes, while numerous faults accommodate deformation within the continental crust. Parts of the northern Andes behave as separate blocks that move relative to stable South America. Offshore, the Nazca Plate continues descending. These different movements overlap across a relatively compact geographic area. As a result, earthquakes in Colombia can occur at very different depths and on very different types of faults. The August 10th earthquake represents one part of this larger tectonic puzzle. That larger puzzle also explains why the earthquake should not automatically be interpreted as a warning that the offshore megathrust is about to rupture. The main subduction interface continues to exist regardless of what happens inside the deeper slab. The Nazca Plate continues moving beneath South America at rates measured in several centimeters per year. Stress continues accumulating in locked sections of the shallow boundary. Large earthquakes have occurred there in the past, including the enormous 1906 Colombia-Ecuador earthquake. But an earthquake 110 kilometers deep inside the slab does not automatically mean that stress has suddenly been transferred to the shallow plate interface in a way that guarantees another major earthquake. At the same time, the deep earthquake does not reduce the long-term earthquake hazard along Colombia's coast. The subduction zone remains active. The plate continues moving. Faults continue storing and releasing strain. Shallow earthquakes, intermediate depth earthquakes, and major interface earthquakes can all occur within the same broad tectonic system. Each mechanism presents a different hazard. A deep earthquake like the August 10th event can produce widespread shaking. A shallow crustal earthquake can cause intense localized destruction. A major offshore megathrust earthquake can produce both devastating shaking and a tsunami. Understanding these distinctions is essential for interpreting what a single earthquake actually tells us about future risk. The deeper significance of the event may ultimately have little to do with whether another earthquake follows it. The August 10th rupture has already demonstrated that the northern portion of the South American subduction system is capable of producing powerful intermediate-depth earthquakes beneath Western Colombia. It has shown that the descending Nazca Plate can undergo major strike-slip deformation at depths exceeding 100 kilometers. It has also highlighted the importance of looking beyond the shallow plate boundary when assessing earthquake hazards in Colombia. A country sitting above a subduction zone can experience destructive earthquakes not only at the interface between plates, but also within the plate that is disappearing into the mantle. That hidden slab is one of the most extraordinary geological structures beneath South America. It begins at the ocean trench and descends beneath the continent, carrying ancient oceanic lithosphere into Earth's interior. As it travels downward, it bends, fractures, heats up, and undergoes chemical and mineral changes. Earthquakes allow scientists to trace portions of that journey indirectly. Every deep earthquake provides information about where the slab is strong enough to rupture and where it has become too hot or weak to generate earthquakes. The August 10th event occurred in a particularly important region near the northern limit of intermediate depth seismicity, making its seismic fingerprints valuable for improving models of the slab's shape and mechanical behavior. The event also demonstrates why magnitude alone cannot describe earthquake danger. A magnitude 7.4 earthquake is unquestionably large, but its consequences depend on depth, distance, geology, construction, and rupture characteristics. A shallow magnitude 7.4 earthquake beneath a densely populated city could produce extreme localized destruction. The same magnitude at 110 kilometers depth can spread shaking across a much wider area while producing a different pattern of damage. The August 10th earthquake combined substantial depth with a large rupture and a region containing vulnerable structures and difficult terrain. The resulting damage shows that intermediate depth earthquakes deserve serious attention even though they behave differently from shallow events. Something huge did indeed move beneath Colombia on August 10th, but the phrase needs to be understood correctly. It was not the entire continent shifting. It was not the Nazca Plate suddenly dropping several miles. It was not evidence of a massive underground void collapsing. A section of the descending oceanic slab experienced sudden fault slip at approximately 110 kilometers or 68 miles depth. The rupture may have extended roughly 105 kilometers or 65 miles across the hidden fault. That movement released enormous seismic energy and sent waves through the earth. For several minutes, a structure that normally moves only centimeters per year underwent sudden deformation. The Nazca Plate is still descending beneath South America. The Andes are still being deformed. The slab is still bending and adjusting at depth. Stress is still being transferred through faults that cannot be seen from the surface. Every year the plates move several centimeters, slowly reshaping the region. Most of that motion is invisible to people living above it. Occasionally, however, a section of the system fails in a matter of seconds, releasing energy that has accumulated through geological processes operating for years, decades, or longer. August 10th was one of those moments. The earthquake did not create Colombia's tectonic danger. It revealed, for a brief and violent interval, just how active the hidden machinery beneath the country remains.